Hello, this is my final project presentation for CSE 611, and the title of the project is Simulated Multi-Objective Optimization of Microarchitecture Performance using Tomasulo's algorithm. And my name is Nicholas Johnson. So, for introduction, the Tomasulo's algorithm is a computer architecture hardware algorithm for instruction scheduling that allows out of order execution, or OOE. And the primary components or features of the algorithm are register renaming, reservation stations, and a common data bus. And you can see those in the figure here. It has the instruction block, the register block, the reservation stations, the functional units, one in this case for adding and subtracting, and one for multiply or divide, as well as a storage bus. And the algorithm has a major performance improvement over the scoreboarding algorithm, which is a much simpler algorithm, which is very centralized. It doesn't handle these two hazards, write after write and write after read, and it does not have register renaming. So Tomasulo's algorithm is much faster. So, in using Tomasulo's algorithm, there's some important hardware considerations, and that is the number of functional units for the adding, subtracting type, and the multiply, divide type. And those exist regardless, but for Tomasulo's algorithm, you need to implement reservation stations as well, which is more components. You need a certain amount of reservation stations for the adders and the multipliers. And as well, in general, you also need to consider the size of the register file. These are all the primary important considerations for the working of this algorithm. And of course, the goal overall is to maximize instructions per cycle, but you want to minimize the cost, like manufacturing, maybe design as well, fabrication. You also want to minimize the power usage, and other things could be like the area, things like that. So there's some trade-offs that could be expected to show up between these objectives: performance and cost, power, etc. So in this project, I simulate Tomasulo's algorithm, and the primary output of that is, given the configuration of the previous components we just talked about, we want to calculate how many cycles does the algorithm take on a given workload. And for the other objectives like cost and power, I don't have direct access or a good approximation model for those metrics. So as like a surrogate metric for cost and energy, I'm using the size or the number of those hardware components. So we want to essentially minimize the number of cycles as well as minimize the number of hardware components, which are two objectives which are in conflict with each other. So a simple optimization would not be extremely simple in that case where you have conflicting objectives. So here's some related work. Many publications in the area of searching design space and optimizing configurations, they use evolutionary algorithms and um, multi-objective evolutionary algorithms to get Pareto fronts. So some examples, this paper is called an FPGA compiler for on-the-fly adaptive CNN deployment and reconfiguration. It's not in the title, but important to the paper is it leverages analytical performance models and multi-objective genetic algorithms to efficiently search large configuration spaces, which is similar to the goal here. Another paper, multi-cube, multi-objective design space exploration of multi-core architectures. This one uses evolutionary algorithms to get Pareto optimal power, performance, and area configurations. So that is quite similar to what we want to do here. Again, conflicting trade-offs, which is the motivation for multi-objective evolutionary algorithms. And last one is NSGA2 based DSE for energy and throughput aware multi-core architectures. This one again uses an evolutionary algorithm, NSGA2, to search trade-offs of energy versus throughput. So these last two very similar, and also similar goals and problems to what this project seeks to investigate. So my proposed method for the project is to investigate the viability of optimizing cost and energy, as well as throughput, or IPC in this case, in a purely simulated environment in architecture configurations with Tomasulo's algorithm. So similar to those other papers, I'll be using NSGA2, which stands for non-dominated sorting genetic algorithm, on the various objectives, which what we do have good simulation access to is the IPC. So we want to maximize IPC, which is similar or the same as minimizing the number of cycles for given a fixed workload. And then the surrogate for cost or energy is minimizing the complexity and or number of hardware components, and that involves having a separate minimization objective for each type of component. And in this method, it's also important to test the objective, the IPC, on a variety of realistic workloads, which is something else that needs to be investigated. So just a little background on NSGA2. The goal, this is a modification of genetic algorithm. It seeks to find a diverse set of Pareto optimal or near Pareto optimal solutions. So in this figure you can see the red line would be the Pareto front, and there's some solutions on it, A, B, and D. These are Pareto optimal because there is no solution, there's no point that is better in one cost or objective without making other ones worse. However, for point C, it's not Pareto optimal because you can get better solutions without making the other ones worse. So, what NSGA2 does is that, like genetic algorithm, it has a population of solutions that evolve over generations. And so, at each generation, it looks at the various population members and it assigns them to different fronts or non dominated fronts in a sorted fashion. So, just given these points in the space, it would assign like the green front is the best, the blue front is the second best. And these are fronts of solutions which are non dominated by points in the later fronts. So, you can rank these like one front is completely non dominated, and then taking that out of consideration, the blue one becomes the next totally non dominated set of solutions, and so on. So the goal is that over time, with the selection, reproduction, and crossover, which is already existing in normal genetic algorithms, using that in tandem with the fronts, you can have the front of the population converge towards the Pareto front. And NSGA2 also has a sharing or crowding mechanism to try to obtain a diverse set of solutions along the Pareto front rather than having the whole population converge to just one point on the Pareto front. So this is really applicable to computer architecture optimization, where you want to have the best possible configurations and good knowledge of all the different trade-offs. So here's the overall process of the genetic algorithm. The base genetic algorithms on the right, and the NSGA2 specific stuff is in this box here, which is non-dominated solutions in a front, and then applying sharing, and then creating the next front in a loop. And the rest of the stuff here, like I said, is just regular genetic algorithm stuff. So some background on Tomasulo's algorithm. It handles read after write with tag broadcasting on a central data bus. You always have to stall for read after write, but you want to be able to recover as quickly as possible, which is what the tag broadcasting does. And write after read and write after write can be handled with tag renaming, so you don't actually always have to stall for those, where scoreboarding might stall. So the algorithm is designed to minimize stalling and maximize the IPC. And again, the primary hardware considerations is the number of functional units for adding and multiplying, the number of reservation stations for those two as well, and the size of the register file. So this is a fairly simple problem or a set of instructions being executed with Tomasulo's algorithm. Just 3 instructions, IJK. It doesn't finish the whole thing, and this figure's messed up. I'll fix it in the slides. It's just showing the beginning stages of the execution, the dispatching and the tags, and where you have to stall and so on. This is essentially the algorithm that I implemented to simulate the workloads, which look something like this. So methodology for this project, again, the optimization objectives for the NSGA2, they're all minimization. We want to minimize the number of cycles that a fixed workload requires, and we want to minimize the number of components in the hardware configuration, and that's one minimization objective for each component type, so that should be 5. which is the functional units, the reservation stations, and the register file size. We want to minimize all of those as a surrogate for cost or energy. And for calculating the number of cycles for some hardware configuration, the method I chose is to generate each time you want to get a metric value for number of cycles, generate 10 workloads with 5,000 instructions each, and among these 10, vary the proportion of raw, write after write, and write after read hazards, and also vary the number of registers used in the programs. So doing this over 10 workloads of a large size should give a good, realistic number for IPC, or we're just calculating number of cycles required because we're fixing the number of instructions. And over these 10 workloads, calculate the average number of cycles, and that is the metric for some hardware configuration when it needs to be calculated. And the goal, the final part of this methodology, is to compare the final population of NSGA2 to the exhaustive search of the whole design space. And we can do that because the design space is pretty limited in this experiment. There's not that many objectives or values that they can take. So for the experiment, first, this is the method of workload generation. I vary the proportion of the different hazards between reasonable values. So when generating one workload, proportions of different hazards are chosen for all the different instructions. So read after write hazards, this is are uniformly selected to be between 10 and 50%, and then write after read hazards are uniformly selected to be between 5 and 35%, and then write after write is chosen to be between 1% and 20%. And it's guaranteed to not go over 100%. There's a cap, otherwise that wouldn't make much sense. And the number of registers used in the program is also varied. So the workload might only involve 8 registers, or it could be all the way up in 128 registers. And the parameters chosen for NSGA2, a crossover, I chose single point crossover with a 90, or that should be 90%. I'll change that. And mutation has a 10% chance to randomly flip all the configuration parameters, which there's 5, so it will there's a 10% chance to randomly select between the number 1 and 5, and that's the number of parameters flipped. This is done because we don't want continuous values or chromosomes. Everything should be discrete, so we're basing things on flips. Selection in NSGA is use tournament selection, and I choose k equals 2. Population size is set to 50, and the number of generations is also set to 50. And again, evaluation, or the fitness metric, is the average number of cycles required on 10 workloads of 5,000 instructions each, and these 10 workloads are generated with these parameters. So the hardware configuration space, or the whole design space, the number of adders can be between 1 and 4. Number of multiplier functional units is either 1 or 2. These are reasonable values that I've found, and the number of reservation stations for each functional unit is between 2 and 6 for adders and multipliers, and the number of registers, the size of the register file, is either 16, 32, or 64. And this isn't an extremely large search space, but the experiment is rather limited itself in what I'm able to do, and these are reasonable values. It wouldn't make sense to add more possible values for configurations which aren't really done in practice. So NSGA2 might seem overkill for a rather limited search space, but it's still moderately large enough that we should get interesting results if all goes well. And so, speaking of results, we have each objective, so 6 objectives, all minimization over the 50 generations. So in the top left, we have the average number of cycles required. This starts high at generation 0, which is a randomly initialized population, and then decreases closer to the end. Similar with the number of adders, it decreases over the generations. The number of reservation stations for adders has a strong decrease. The reservation stations for multipliers is more spiky, volatile. It goes down and up a few times, but it ends up quite low. The number of multiplier functional units actually increases, has a general increasing trend. It does go up and down a few times, but it ends up higher than it was. And the number of registers in the register file size, overall, it ends up lower than where it started. But there is a moderate spike up in the middle. So most of the objectives have an overall strong downward trend. A couple of them start to increase towards the end, like these two, the red and blue, number of cycles and number of adders. And the reason why an objective would start to increase is that others need to decrease, and the evolutionary algorithm is working through the trade-off of how can we decrease these other objectives if it requires an increase in the others, what's the optimal trade-off? That's what the evolutionary algorithm is doing here, and we can see that because it minimizes the objective and then increases a little bit to make room for other objectives to lower as well. The only objective that had a strong increasing trend was the number of multiplication functional units, and there was only 2 options for this, either 2 functional units or 1, and the algorithm or the evolution certainly favored using 2 functional units, because we'll see the difference in performance between 2 and 1 is incredibly large. So the evolution decided to heavily favor this trade-off in using both, or using 2 functional units for multiplication, because the difference is extremely stark, because multiplication takes more cycles. This plot shows it's sort of a way to calculate or visualize the diversity of solutions. It uses a test knee, which takes the whole configuration of a solution and reduces it to 2 dimensions using like latent factors. And this is linked testing, which sort of makes these not independent. It's temporally linked. So you can see in generation 1, there's about 3 clusters of solutions in the latent space compared to generation 50, which has more spread around the latent space. So that's the main takeaway here, is that NSGA is getting diverse solutions, which is good. It's what we want to see. We want to capture all the trade-offs possible. So this is a comparison of the final population, which is 50 solutions or configurations for the NSGA2, comparing that to the entire search space. So looking at the top 5 solutions sorted by number of cycles required for the whole search space, you can see this is the best configuration found, which it has the maximum number of adders, multipliers, reservation stations, and it has a large value for number of registers, but not the maximum. So as you would expect, the best IPC is achieved by using the most components of everything you have available. And also in the other top 5, this is out of the entire search space, it's using a large number of components. Like reservation stations, it's always using the maximum amount. For adders, it's using 4 here again. These might be outliers using only 1. Maybe it has a small impact. But comparing that to the top 5 solutions, again, sorted by number of cycles in the population, you can see the NSGA2, the highest IPC population member, does not have the maximum reservation stations or number of registers, and overall the number of components used is lower in this. For the best IPC configurations, however, the IPC is a little bit higher, but not extremely so. The range of number of cycles in the entire search space is quite large. So a difference of in the range of tens or maybe 100 cycles is not that significant if you consider these components to have a large cost or energy penalty. So yeah, in overall, this comparison shows that the NSGA2 population, the best IPC solutions have slightly worse IPC than what's possible in the whole search space, but the ones chosen have less components. So it's a decent trade-off, or I would say it's a good trade-off actually, because the IPC increase for these is actually quite low. So the NSGA2 is identifying the really good trade-off areas in the search space where you can have a tiny or less significant penalty in one objective for moderate to good gains in another objective. So conclusions. Number 1 is viability was demonstrated in using NSGA2 to find a diverse set of near Pareto optimal hardware configurations for architectures using Tomasulo's algorithm. And this is backed up by the results we just looked at, where a diverse set of good solutions with trade offs was found. However, number two, the correspondence between the number or complexity of hardware components and the cost or energy or area, other real world objectives, that correspondence is still an assumption. More in depth experiments often use simulated metrics for cost and energy, etc., but they are much more complex. They often have like hybrid metrics. For example, some of the ones I looked at used like regression. So if you can imagine, you're trying to have an objective for area that could have variables such as cache size, for example, or energy could relate to strongly to the number of cores in some other experiment. Things like that often use learned metrics, which for the purpose of this experiment was not so easy to do because of I would say its simplicity. But we still did demonstrate viability. But for number three, larger design search space and a larger design search space and access to more empirical optimization objectives would make NSGA2 more practically useful. So again, our search space was quite small, and our using a very simple surrogate of the number of components and size of register file as a metric for cost or energy was kind of a strong assumption with not a lot of empirical backing like metrics you would see for more complicated experiments. But it still would be useful to use NSGA2, and it has been used in many areas. If there was a slightly larger experiment, which also included Tomasulo's algorithm, that could be done with more complex metrics. And it's useful to use these evolutionary algorithms in general for computer architecture design, because when your search space is incredibly large, the evolutionary algorithm, specifically NSGA2, is able to go through the search space with only a few configurations at a time and converge to nearly optimal trade-offs at the Pareto front. And you only have to simulate the configurations in the population on demand as the evolution progresses. So overall, I would say the project was a success based on the results. They did show what was expected to see out of using an evolutionary algorithm to get these trade-off results. And the evolutionary algorithm did find good solutions with what would be considered like a surrogate interpretation of lower cost at the penalty of slightly worse throughput. So I think that's it. Here's the references. Number one is Tomasulo's algorithm, and the others are papers I looked at for how they use NSGA2 and set up experiments for design space exploration and so on. So thank you.